Hi, hello everyone. This is Dr. Chiranjeevi Manike, Professor and Head of Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. As part of data mining video lecture series, in this lecture, we are gonna discuss about data transformation and data discretization. So this is one concept in data pre-processing. This is the last concept in first unit. So in this lecture, we are mainly going to discuss various data transformation strategies, and one of the data transformation process, that is data discretization, and the concept representation, that is in the form of hierarchy. So first, let us try to understand what do you mean by this data transformation. So very beginning, we discussed about the importance of the data transformation, like why we need to transform the data. So what format the available data will be, and what format need to be converted into. So because we cannot directly apply any data mining or any exploratory analysis or any other data analysis techniques or analysis techniques on the raw data. So this raw data need to be transformed into the required format. So for that, the data transformation need to be done. So here the data are transformed or consolidated so that the resulting mining process may be more efficient and the patterns found may be easier to understand. So these are the two major objectives of data transformation. So to make the data mining process more efficient and to understand, we can easily interpret the mining results. Those are the patterns. So here in this data transformation, we are going to discuss various strategies like smoothing, attribute construction, aggregation, normalization, and also the discretization. Next concept, the concept hierarchy generation for nominal data. So let us see one by one. So smoothing, this is one data transformation strategy, so which removes the noisy data, that is removes the noise from the data. So we already discussed what is the noise, what in the previous data pre-processing and data cleaning techniques. So this noise removal, the techniques includes the binning, regression, and the clustering. So next strategy is attribute construction. So this in detail we already discussed in the previous lecture, and this is also called as a feature construction. So features are nothing but attributes, are the characteristics which are used to describe data. Like suppose most of the time, suppose the data set, the columns, wherever the columns attributes as the features. Okay, so these are the instances, samples, or the tuples. Tuples or instances, samples, etc. So attribute construction, it is a feature construction. Sometimes we have to create a new features or new attributes, or sometimes we have to combine the available attributes so that we will create a new set of attributes and we will improve the quality of the predictions or analysis. So, and we also, one more important thing that we already discussed is all the features or attributes in a data set may not be equally important. Even few attributes may not even contribute, not at all correlated to the target. So in that case, we can simply omit or discard those attributes. The rest of the attributes may contribute, but all the attributes, the rest of the attributes may not equally contribute. Like suppose, let us say x1, x2, x3, these are the three attributes, and this, the contribution may be like some 60%, and this some 20 percentage, and this some 10 percentage, like this. That means, so this attribute is going to influence the target variable more, 60 percentage. And similarly, this second attribute x2, that is also going to influence, but the 20 percentage. So in this attribute construction, we will do all this kind of analysis. So we'll construct new attributes and we'll add those attributes from the given set of attributes. The next data transformation strategy is aggregation. So where the summary or the aggregation operations are applied, like average, sum, etc., to the data. So these are typically used in constructing a data cubes, because in data cubes, the different dimensions, and in each dimension there will be different attributes, so that we could do some multi-dimensional analysis by using the data cubes. And like the hierarchy, like the abstraction level of abstraction, like suppose if you want the total yearly sales information, so you can get this total year sales information from the quarters, quarter 1, quarter 2, quarter 3, like this. Next data transformation strategy is a normalization, and this is another very important. So most of the time in machine learning and deep learning, we use this normalization, because here where the attribute data are scaled to fall with a smaller range, such as 1 to 1 or 0 to 1. So for example, if we take a data set, so the data set D, has some set of attributes like age, salary, etc. So the age values, the set of all possible values for this attribute age would be, let us say, like some 1 to 80. Okay, 1 to 80. And if you take the salary attribute, the values, the set of all possible values for this attribute would be, let us say, like all the employees' salaries more than 1 lakh. So more than 1 lakh to, let us say, some 10 lakhs. So in this case, this range dominates the values of this age attributes. Okay, the values of salary attribute dominates the values of age attribute. In this case, we have to normalize so that we can clearly understand the correlation between the age and the salary or any other attributes which have the very small ranges. So next, data discretization. This is one of the data transformation technique. So where the raw values of a numeric attributes, for example age, are replaced by the interval labels, example 0 to 10, 11 to 20, etc. And also the conceptual labels, example youth, adult, and senior. And another strategy, data transformation strategy, is a concept hierarchy generation for nominal data. Here, where attributes such as the street can be generalized to the higher level concepts like city, country, continent, etc. So many hierarchies for the nominal attributes are implicit within the database schema and can be automatically defined at the schema definition level. So here, these are mainly the concept hierarchies will be used to represent this nominal data. So we already discussed the different types of attributes and their values. So let us just discuss in detail about this data discretization technique. So data discretization techniques can be categorized based on how the discretization is performed, such as whether it uses the class information or not. So if a discretization technique uses a class information. So that means, so like suppose if you take a data set, so it has attributes like, and this is a class label or the response or class label. Response or class label. So if we use any discretization technique that is uses the class information. Okay, so like there will be n number of samples in this data set. So each sample would be assigned a class label. Okay, these are the class labels. So this discretization technique uses this class information. So then that is called as a supervised discretization technique. If not, that means this discretization technique do not use the class information. So then that is called as a unsupervised discretization. So let us see in detail about this the construction, the discretization technique would be applied with a simple numerical example. If the process starts by first finding one or a few points, those points are called as a split points or the cut points, to split the entire attribute range and then repeats this recursively on the resulting interval, and that is called as a top-down discretization or splitting. So for example, here you can see, let us take one age data set. This is age data set. So it has the age values 18, 25, 35, 42, etc. So here we'll start with, because it is a top-down approach, so we'll start with the values like 18, that is the starting value, that is minimum value and maximum, or the minimum age and max age in this from this data set. So then we'll identify the split point or the cut points. So based on that is, let us say like 35, the cut point, so 35, and based on the 35 we would split this into the two bins, let us say 2 bins, and again this process will be repeated. Again here, again we'll identify the cut point and then we'll divide this into the bins. So this process would be continued until we meet the stopping criteria, like let us say the number of bins in this case. So the number of bins is equal to 3. So we have to, like suppose this is a threshold value or the stopping criteria. So once we meet the stopping criteria, we have to stop the construction, like splitting this data. Okay, so this is, we are following, this is the top down discretization or splitting. So here from this we can see easily, it starts from the higher level and these are the detail. Next, another type of a discretization is a bottom up discretization, and this is also called as a merging. So which starts by considering all of the continuous values as potential split points, and that removes the sum by merging the neighborhood values from the intervals, and then recursively applies this process to the resulting intervals. For example, if you could take the merging like a temperature data, and these are the temperature values. So here we have to start by considering all of the continuous values as a potential splitting points. So that's why we have considered all the continuous values here. So then we are going to apply the merging. So that is remove. We have to identify the neighborhood values, and then we'll identify the intervals, then recursively apply this process. So in this way, and these are all right here from this first step 1, each value, right, would be considered as a potential split point. So then we will identify, and based on the neighborhood values, and we could perform the merging, so that the 10 12 would be merged, 15 14 15 and 18 20, like so. These are the values we are going to merge. So here this. So this same the stopping criteria, like one stopping criteria is the number of values in each bin, or the number of bins. So based on that, we could continue this top down and the bottom up discretization. Next, the data transformation. This is one of the important technique, that is normalization. So the measurement unit used can affect the analysis. Like suppose, for example, if you want to measure height, suppose if you want to measure the height, so we could use the measurement unit as like centimeters or meters. So then we'll get some values. Suppose we replace this unit, measurement unit, like instead of meters, if we use inches, then we'll get some set of little bit more values. In place of inches, if you could use centimeters, then we'll get more values. Instead of centimeters, if we use the millimeters, then so we are going to have the many values. So that means if you change the measurement unit, it could affect the data analysis. So how we can avoid this? How the normalization technique would help us to avoid this kind of dependence, because the analysis depends on the measurement unit. Okay, so measurement unit is going to affect the analysis. So how we could avoid this dependency? So that is on the choice of measurement units. So to avoid that, the data should be normalized or standardized. So what do you mean by normalized and standardized, and what are the different techniques in normalization? So normalizing the data attempts to give all attributes an equal weight. Like just now before we discussed about the two attributes in a data set, age and the salary. The salary, the range is very high, so dominating all the values. So that to give equal importance or weightage to each attribute, so we apply this normalization. So in this normalization, so there are three techniques we use. One is a min-max normalization. Second, Z-score normalization. This is also called as a zero mean normalization. The third one is a decimal scale. So for example here, the min-max normalization, and this is a data set. This is data set. So it has attributes like employee, EMP, age and salary. So there are 7 samples, 7 tuples in this data set. So now we are going to apply the normalization to this data set. Here you can see, right, by seeing these values, you could understand this range is large, right? It's a big one compared to the age. So we have to apply the normalization. So let us see how this is very simple. And this is a formula we use to find the norm of any value. Like for example, in this case, x norm equal to x minus minimum of x and max of x minus min of x. So for example, to calculate the normalized value where x equal to 35, and the minimum value of this, right, the minimum value is 27 and the maximum value is a 48. So minimum value is 27, max equal to 48 for this age column. So now the x norm for this 35 age would be calculated. Right, you are going to supply the values for these variables. Here 35 minus min is 27 and then max is 48 minus min is 27. So we'll get this normalized age value. Similarly, we could apply this normalization to the all values in the data set. So this is the way, so that you can see the age and we also normalize the salary. This is a normalized value of a salary. So we can see that these are the we are given the equal weightage. So 0.14 or the age value here 0.19, so that we can easily understand the correlation between the attribute age and the salaries if we could normalize the data. Next one is a Z-score normalization. So Z-score normalization, this is also called as a zero mean normalization. So here the formula to calculate this Z-score equal to, so here we have to find out the standard deviation and mean. So then we substitute the values here, then we'll get a Z-score. The next one is a decimal scaling. So decimal scaling that normalizes by moving the decimal point of values of a attribute. So the number of decimal points moved that need to be moved depends on the maximum absolute value of A. Maximum absolute value of A. For example, let us say Vi is a value and this is a decimal. After applying the decimal scaling, and this is the value. So here the Vi, let us say Vi is a value under the attribute A, and this value is Vi, the max of, okay, so max of Vi, that should be greater than 1. That should be greater than 1. So that means how many points, decimal points need to be moved. That will be decided based on the maximum absolute value of A. So for example, here 987 is minus 987 is a one value and 700 is another value, positive value. So in this case, maximum absolute value 987 would be divided by 1000, so then it will be equal to 0987. Okay, so this is a way we can move the decimal point. So moving how many decimal points need to be moved, that is completely depends on the maximum absolute value of A. So next there are other data transformation techniques like data discretization by binning, discretization by the histogram analysis, discretization by the cluster, decision tree, correlation analysis. These are all we already discussed in the previous lectures. Next concept is the concept hierarchy generation for nominal data. That is the specification of a partial ordering of attributes explicitly at the schema level by users or experts. So while defining a schema So we have to explicitly specify the level. For example, let us take a relational database. The relational database has the set of attributes like a street, city, provenance, or state and country. And there is a data warehouse. Data warehouse has a dimension location, which also includes the attributes street, city, provenance or state, and country. So we can create the schema with all these levels like street, city, state or provenance, country, location, so that we can perform this hierarchies, levels. We can represent this in the form of a concept hierarchy. So specification of a portion of hierarchy by explicit data grouping, and specification of set of attributes but not of their partial ordering. So these are the other concepts to generate the concept hierarchy for nominal data. So we could explicitly specify portion of hierarchies while creating the data grouping. And another one is the specification of set of attributes but not there of a partial ordering. So like we could add the intermediate values in between to increase the granularity. So let us quickly summarize what we have discussed in this lecture. So data transformation routines mainly converts the data into appropriate forms for data mining. And we already discussed the data discretization and the concept hierarchies generation. These are also forms of data reduction. The data discretization transforms the numeric data by mapping values to the interval or a concept labels. Whereas the concept hierarchies are also useful for mining at multiple abstraction levels. So there are many other concept hierarchies like can be defined for the same attribute to accommodate the needs of various users. So thank you for watching.